Alright, so let's talk about organometallic chemistry. So organometallic chemistry is simply the chemistry of organic compound and metallic compounds that are bonded together chemically. So they have the metal to carbon bond. It's important to note that. So looking at the examples here, let's start with this. So the carbon of the organic compound is chemically bonded to the metal here. So this is an example of organometallic compound. So looking at this also bonded to the carbons of this organic compound. So this is simply CH2, CH and CH2, but with double bond, and there is a resonance there, right? So the platinum is this metal here is bonded to the carbon of this organic compound. So looking at this also, iron is bonded to carbon of carbon monoxide, and looking at this also, the iron is bonded to carbon, 6 carbon in this case. So classification of organometallic compound. So organometallic compounds, particularly those of transition metals, can actually be classified based on the number of carbon atoms of the organic compound that are directly bonded to the metal. So looking at this, in this case, only one carbon is bonded to the metal A. So we represent this with hapticity value of 1. So the classification here leads to the concept of hapticity. So let's put it there, hapticity. So hapticity basically describes the number of carbon atoms that are directly bonded to the metal atom, right? So in this case, one carbon atom is directly bonded to the metal here. So the hapticity is 1. It's monoactive. The hapticity is 1. So looking at this also, this is similar to CH2 and then CH3. So even though we are having 2 here, the hapticity here is still 1 because only one carbon is bonded directly to the metal here. So but in this case, we have 3 carbons. There's a resonance here. So 3 carbons are bonded to the metal here. So the hapticity here is 3. So looking at this also, in this case, the hapticity is 6. There's a resonance there. So 6 carbons are bonded directly to the metal here. So also looking at this, 1 carbon is bonded to the iron here. So the hapticity is basically 1 there. So it's important to note that. So now let's talk about the stability of organometallic compound. So in order to describe the stability of organometallic compound, there is a rule that has been put forward, which is the 18 electron rules. So I come up with these mnemonics to make the understanding better. So VAR shakes 1-2 carbons added. So just know this, and then you'll be able to determine the stability of organometallic compound. So let's break this down. The VAR there, so it simply has to do with the valence electrons, right? So the VAR here is the valence electron. So you need to count the number of valence electrons of the central metal in 0 oxidation state. So looking at this, this is the central metal, right? So the oxidation state of this in ground state, equals to 10 electrons, because recall that this is a group 10 element. So the valence electron of this central metal is 10 electrons, right? So the next thing you need to check for is the charge. So you check for the charge. So how do you determine the charge? So let's say we have the structure here. This is a neutral compound, right? So assuming, using for an example, let's say we have plus here, then it is a charge. Or let's say we have negative, it is a charge. Let's say we have 2 negative, or let's say we have 2 positive. These are charges, right? So if it is 2 positive, we are subtracting 2 from this, right? But if it is 2 negative, we are adding 2 to the ground state value. But in the case where it is neutral, we are adding nothing to the ground state value, right? So the next thing you need to do is to count electrons. Count 1 electron for covalent bond. So this is best determined when you try to draw the structure, right? So let's say we have PD. This is let me use another pen. So let's say we have PD. So let's say we have this is chlorine, right, for this. So this is let's say phosphorus. Okay, so we have phosphorus that is bonded to, so we have 2, 3, and 4. So phosphorus that is bonded to phenyl group. So let's say we have it this way. Phosphorus that is bonded to phenyl group, and let's say we have this here, which is this. So you do not have to draw the structure, but I'm just trying to pull this out so we can understand what we're trying to do here. So count 1 electron for covalent bond. So it's important to note that this kind of bond here, chlorine bond with this here, is covalent bond. So we have PD chlorine, you add 1 electron, right? The covalent bond. So here also the metal to this phosphorus phenyl is the active bond. So you need to note this. This is similar to having ammonia, right, which have a lone pair of electrons. So this also have a lone pair of electrons. So this makes it possible for it to undergo the active bond. So PPH3. So this is the active bond, right? So we have 2 here. So we are simply putting 2. That will be 2 times 2. That will be 4 electrons, right? So the next thing we need to look at is the hapticity. So this is simply the count 1 electron per delocalized carbon fragment. So the hapticity here is 3. So basically the bond also will be 3 electrons, right? So let's put it there. PD C3H5. So the electron count is 3. So now let's add everything together. So this will give us, we have 10, 11 plus 4, that is 15, plus 3, 18. So we have 18 electrons. So it has 18 electrons, that means it is stable, right? So the compound is stable and will exist. So take note of that. So let's look at